Good afternoon, students. So we are seeing extraction of metal. So we have three steps: concentration of the ore, extraction of crude metal, and then refining of crude metal. So we already completed concentration of the ore. So second step is extraction of crude metal, which contains two parts. So first part, converting the ore into metal oxide, that is already we have completed in the last video. That is, we have roasting and then calcination. So now today we are going to see in this video how do you convert this oxide ore to metal. That is reduction of metal oxide to metal. That's our topic for today's discussion. So reduction of metal oxide. So how do you reduce it? By using suitable reducing agent. Okay, so examples are carbon, carbon monoxide, hydrogen, aluminum. Each case we are going to see one by one. Okay, so we'll just continue. So first we'll see smelting process. Okay, this is a technical term used for reduction. Okay, so smelting process. In this method, a flux. So in this method, we actually use two components. One is a flux and the other one is a reducing agent. So you know what is a reducing agent? It converts metal oxide to metal. Okay, and what is the flux? So flux is a substance added to this mixture during smelting. It has two functions. First function is it reduces the fusion temperature as we use metals. Okay, so when you are going to melt metal, we use very high temperature. So if you use flux, it will reduce the fusion temperature, that can save energy. Second thing, this flux will combine with gangue or other impurities and convert them into slag. So what do you call slag? Unwanted impurities formed in the extraction. In Tamil we call it as kazhuvinir. Hope you understand. The unwanted waste coming out from the industrial waste. So that we call it slag. So flux helps in two ways: decreasing the fusion temperature and removing the slag. Okay. So now we'll just move on to this. We'll take an example. Okay. The extraction of iron from hematite ore. The formula is Fe2O3. Carbon monoxide is used as reducing agent. So you can just see in this case, carbon monoxide combines with oxygen, it removes oxygen. Okay. So carbon monoxide and oxygen gives you carbon dioxide, and iron present in 3+ oxidation state is reduced to iron 0 oxidation state. As I told you in the last video, metal in valency, when they have valency, they are present as salt in the combined form. Once they lose or once they gain electron, when they are in 0 oxidation state, they become strong metal. Okay, so this is how we go for extraction of iron. So in this process, if you see, the impurity present is removed by using flux. So in this extraction, you see a basic flux limestone is used. So there are two types of flux: acidic flux and then basic flux. So what is this? Why we use such kind of flux? See, if the impurity present in the extraction is going to be acidic, say for example in this extraction, silica SiO2 is present as gangue or impurity, and this we call it as acidic gangue. The reason is non-metallic oxide form acidic, okay, and metallic oxide form basic. So in this case, silica SiO2, silicon dioxide present as gangue. So we have to choose a flux which is basic in nature, that is calcium oxide. So this we call it as basic flux because metal oxides are basic in nature. Okay, so this will combine with this to form slag, calcium silicate. The name is chemical name is calcium silicate. The equation is very simple, just add them and write 1 Ca, 1 Si and 3 oxygen, CaSiO3. So in the previous case we didn't balance the equation, we just go for balancing equation. Very simple. Here we have 2 Fe, here we have 1, so I put 2 in the front. Iron is balanced. Now carbon monoxide takes oxygen from Fe2O3, right? Okay, one carbon monoxide can take one oxygen to make it carbon dioxide. Am I right? Okay, so one carbon monoxide takes one oxygen to make carbon dioxide, but the formula says we have 3 oxygen. So how many carbon monoxide we need? 3 carbon monoxide. So you put 3 over here. Once you put 3 over here, carbon is 3, so put 3 over here, equation is balanced. Is it okay? So we'll just continue. Next we'll just see in the extraction of copper. First we have completed iron, now we'll go for copper. In the extraction of copper from copper pyrite. So we have equation in this part. So we'll just learn the equation. We have 5 equations. So the important question exam point of view. So I want you to learn the equations. So we'll just see copper pyrite, CuFeS2. Okay, this is also called as mixed sulfide ore, CuFeS2. When roasted, so oxidation takes place, roasting, you know what is roasting, heat in presence of oxygen. Okay, so now what happens, you see, copper with sulfur forms cuprous sulfide. Just write the values in the top. Copper is 2 plus here, iron is 2 plus here, sulfur is minus 2. Is the electron neutrality balanced? Yes, because 2 2s are 4 minus 2 plus 2 plus 4 plus, so is 0. So next, in this case, copper is 1 plus, sulfur is 2 minus. When you crisscross, Cu2S. Okay, cuprous sulfide. Next, iron with sulfur, ferrous sulfide, FeS. Fe2 plus, sulfur 2 minus, they get cancelled, FeS is the formula. Next, sulfur with oxygen gives you sulfur dioxide. Sulfur with oxygen, the formula what we know is sulfur dioxide. So this is the right equation. Now we'll go for balancing equation. Okay, 1 copper, here we have 2 copper, so I put 2 in the front. Next, 2 iron, here we have 1 iron, I put 2 in the front. Now copper and iron balances, we go for sulfur. 2 2s are 4 sulfur, 1 plus 3 plus 1. 1 plus 2 plus 1 will make it 4. Again, sulfur is also balanced. Now we'll go for oxygen. 2 oxygen, there we have 2 oxygen. Balanced. The equation is balanced. Is it okay? So next, what happens in this case, you see, this ferrous sulfide form will combine with oxygen. This ferrous sulfide form will combine with oxygen. Fe with O, what do you call it as? FeO. Sulfur with O, sulfur dioxide. Fe2 plus, oxygen 2 minus, they get cancelled, formula is FeO. Okay, so ferrous with oxygen, ferrous oxide, sulfur dioxide. Okay, we'll go for equation, balancing equation. 1 iron, 1 iron, 1 sulfur, 1 sulfur. Oxygen we have 1 plus 2, 3 right side. I need 3 left side. So what I put? I put 3. If I put 3, it becomes double, right? So we need 3, so what do you do? Divide by 2. Okay, now equation should not have a fraction. To cancel this 2, I multiply throughout by 2. So 2 in the front, 2 gets cancelled, 2 and then 2. Remember this method? Yes, fractional balancing equation, method of balancing equation. I told you in the previous video, if you learn one equation, you can use in many places. Okay, fractional method of balancing equation. Now, next, once this FeO form, this FeO combines with silica SiO2. This is what the flux added here. This is what the flux added in this extraction, and this is going to be the gangue or impurity. The gangue or impurity form, we will combine with flux. What will be the answer? Just combine them and write, okay? Fe, Si, 2 plus 1, O3. So what do you call this compound as? Ferrous silicate, nothing but slag. It deposits down in the furnace, so this you call it as slag, which is removed. Okay, so ferrous silicate. So this is what is happening to the impurity. Now you just see what type of flux is this? Acidic flux, because the gangue formed is going to be basic in nature. Metal oxides are basic in nature, so this flux is going to be acidic in nature. So we get ferrosilicate. Now what happens to the ore? This is what we need actually. Okay, this cuprous sulfide, you just see this cuprous sulfide. We are talking about the waste going out. Now the ore combined with oxygen. Okay. What happens? A part of cuprous sulfide, okay, not the whole of cuprous sulfide, a part of cuprous sulfide will react with oxygen, forming cuprous oxide and sulfur dioxide. CuO, 2O, because 2 minus 1 plus cuprous oxide, plus sulfur dioxide, SO2. Quite similar method, fractional way of balancing equation. So 2 copper, 1 sulfur, only oxygen is not balanced, 2 left side, 3 right side. So what do you do now? We put 3 in the left side. See, quite similar, no? Balancing. It becomes 6, divide by 2. To cancel this 2, multiply throughout by 2. So 2 gets cancelled, 2 and 2 equation balanced. Okay. So now next step you see, this cuprous oxide form will react with unreacted cuprous sulfide. I told you a part is being converted. So this cuprous oxide form reacts with unreacted cuprous sulfide, because everything will be the same furnace. Okay. Now copper is displaced separately. Sulfur combines with oxygen, forming sulfur dioxide. Go for balancing equation. Oxygen 1 in number, oxygen 2 in number, put 2 in the front, and copper 2 plus 2, 2 2s are 4, 4 plus 2, 6, 6 copper. Now we have got copper. Okay, so this copper you call it as blister copper. Is it okay? Equations are okay? Fine? Okay, now we will go to the textbook. We will go to the textbook. And you should learn the notes also, wait, notes also. Okay, notes also important in this, so please mark this, it's important, exam point of view. Extraction of copper can be asked. Okay, in the extraction of copper from copper pyrite, the concentrated ore is heated in the reverberatory furnace, type of furnace. After mixing with silica, so silica is going to be acidic flux, I showed you in the equation, see, silica is wrongly printed here, this is going to be flux and this is going to be GAN, okay, you can change it, fine. So, silica acidic flux. The ferrous oxide formed due to melting in basic in nature, this is basic in nature, and combined with silica to form ferrosilicate, this is slag. Okay, what you have seen in the equation, you are going to write in the notes. Okay, the remaining metal sulfide. So, what they are trying to say, in this you just see, ferrous sulfide and cuprous sulfide is obtained as a product in the first case, in which a part of ferrous sulfide only will be converted to slag. Some ferrous sulfide is left behind, it will be taken in the next step. Okay. So, ferrous sulfide and then cuprous sulfide mutually soluble to form copper matte. It's a technical term. Okay, see at the end of this process, this 3 step, what will happen? 2 layers will be formed in the furnace. The bottom layer is called slag, nothing but ferrosilicate is removed. The upper layer we call it as copper matte. It's a technical term given. What does copper matte consist of? It consists of chiefly cuprous sulfide, some unreacted ferrous sulfide. Okay, so this is what we call copper matte. So it can be asked in 2 marks, what is copper matte? So you can also highlight this. This is how you have to prepare. Okay, so we'll just go to the next part. So you just see, the matte is separated from slag. The slag is taken out and fed into converting furnace. It's also called as Bessemer converter. We have learnt in 11th standard what is Bessemer converter. During conversion, ferrous sulfide present in the matte is first oxidized. Same process will repeat. Okay, the same process will repeat. Leftover ferrous sulfide will be converted, removed as slag. Okay, we will repeat. Oxide, it is removed as slag formation with the silica. Okay, the remaining copper sulfide, the last 2 equation. Okay, is further oxidized to its oxide. Remaining actually, no, there is a mistake in the book. It should be cuprous oxide. Okay, we just change that. Slag. The remaining copper sulfide is further oxidized to oxide, which is subsequently converted to metallic copper. Okay, so this copper what you get, you call it as blister copper. Okay, now name is, okay, so yeah, over here. This you call it as blister copper. Okay, so why they give this name means, you just imagine that a metal in the liquid state, how viscous it will be, right? Semi-solid form. Okay, a metal in the liquid state. It's copper metal in the liquid state. If you see all this equation, in all the equations, sulfur dioxide is formed as one of the byproduct, which is the gas. Okay, so during this process, the sulfur dioxide trapped inside the solution in the liquid form, solid liquid form, they try to come up to the surface. If it is water, it bubbles up very easily, but semi-solid content. Okay, so how it will come out? With great difficulty. So when they come to the surface of the copper metal is like that. When the bubble comes to the surface, it forms blister-like appearance. Okay, it forms like, when they come to the surface, it forms bubbles in the top. When you see from outside, it looks like blister being formed. When you get a fire wood, you get blister, right? Okay, it looks like this. So that the name is given as blister copper. Okay, so next, once it forms it, then we go for the last step in the extraction. What is that? Electrolytic refining. Okay, that we'll see in the next topic. Fine, just continue. An important question, you are supposed to write till blister copper. Till here you should write the answer. Okay, can be asked in single 5-mark answer. Okay. Next we'll see reduction by carbon. Okay, using reducing agent reduction by carbon, very easy answer. We'll take one equation to explain. Say metals like zinc. Okay, so zinc oxide is here, can be reduced to zinc by using carbon as a reducing agent. So what is the equation? Very simple. Carbon removes oxygen to form carbon monoxide and zinc is displaced. So carbon displaces zinc from zinc oxide. Okay, so we call this carbon as reducing agent. The reason is, see, zinc oxide is actually lost oxygen, right? Can you see here? Zinc oxide has lost oxygen. What is loss of oxygen called as reduction? And who is responsible for this reduction? Carbon has taken it. So carbon is responsible. So we call carbon as reducing agent. You understand? And the equation is self-balanced. So it is enough. Just read the notes, you will understand it. Next we will go reduction by hydrogen. Okay, again hydrogen is also one more reducing agent. So only thing you have to choose what metal you are going to extract and which will be the proper exact reducing agents. Okay, so next some metals which are less electropositive than hydrogen, then you can go for reduction by hydrogen. Okay, for example, if you take zinc oxide, I can't use hydrogen to reduce zinc because zinc is more electropositive than hydrogen. Hydrogen cannot displace zinc, but it can displace silver, it can displace iron. Okay, the example given over here. Quite similar equation what we saw the silver oxide. When treated with hydrogen, hydrogen displaces silver, oxygen is taken, so you get water form and then Ag. So how do you get this formula? Silver is +1 valency, oxygen is -2. When you crisscross, Ag2O. This is how we got the formula. And here Ag Ag is the solid state which has 0 oxygen state metal. And this is the combined form salt, and this is the metallic silver being obtained. Okay, and one more example you can see nickel oxide can be reduced to nickel by using mixture of hydrogen carbon monoxide. Nickel oxide can be done like this: the carbon monoxide and then hydrogen. Now you just see carbon monoxide combined with oxygen to form carbon dioxide, hydrogen combined with oxygen to form water. So we need 2 oxygen, right? 1 to carbon monoxide, 1 to H2O. So I take 2 molecules of NiO. Okay, so 1 over here, 1 over there, and then 2 nickel. Equation is balanced. Clear? So next we'll pass on to the reduction by metal. Okay, reduction by metal. So you can also use another metal to reduce metal oxide. Okay, so this we call it as we go for aluminothermite process. Example, chromic oxide. When you want to extract chromium, okay, that is the reduction of chromium from chromic oxide, we go for aluminothermite process. I just explain the process. What is aluminothermite process? Just click it. Okay, so we'll go for aluminothermic or aluminothermite process. Okay, so in this aluminothermite process they go like this. Okay, the chromic oxide, the metal oxide, is mixed with aluminium. Okay, and Cr2O3 plus aluminium is taken in fire clay crucible. This is what we call fire clay crucible. You can just see 2 over here, that is fire clay crucible. Okay, so what is fire clay crucible? It's just an apparent or instrument or apparent vessel. You can say vessel. I'll just show you the image of what is fire clay crucible. Okay, so this is the click. This is the fire clay crucible. Okay, so it just look like this. Okay, this is a fire clay crucible used in industries. Fine, you can go back. Okay, so they take the fire clay crucible. Over this, they keep barium peroxide and magnesium powder. So it burns very well. Okay, it is used to ignite the content to reach very high temperature. Okay, barium peroxide, magnesium is placed over it, and then using magnesium ribbon. This you could have seen how you burst crackers. You have a wick or a ribbon, right, to burst a cracker, just like that. Now to ignite it, you have a magnesium ribbon inserted. So when you lit it, what will happen? This burns with a very high temperature. At this high temperature, what will happen? Chromic oxide fuses with aluminium. Equation is very simple. I'll just show you. Cr2O3 plus aluminium. Okay. When you heat it high temperature, what will happen? Aluminium displaces chromium. Luckily, both have same valency. You can just see 3 plus chromium, 3 plus aluminium. Okay. Actually, here aluminium is 0. Valency is 0 because free occurring state. When aluminium displaces chromium, it becomes 3 plus. Oxygen is 2 minus. So formula will be just quite similar. Just change chromium to aluminium. Al2O3, same formula. Instead of chromium, I put aluminium plus chromium. 0 oxygen state. Aluminium is going to be 3 plus. Oxygen is 2 minus. You understand? This reaction will take place at a very high temperature. The temperature is reached by barium peroxide and magnesium powder. Okay. And this barium peroxide and magnesium powder, they undergo reaction actually. Okay, that is magnesium take oxygen to form magnesium oxide and barium form barium oxide. The equations are given in the textbook, and this chemical reaction produces large amount of energy. So we'll go back to the textbook. Textbook, just click. Okay, you can just see it. Okay, barium peroxide reacting with magnesium. Magnesium takes one oxygen and forms magnesium oxide, barium oxide. Okay, this reaction is highly exothermic. It produces large amount of heat. At this temperature, chromium is displaced by aluminium. This is what we call aluminothermite process. Important question, exam point of view. So please mark it. You have to write till here. Okay, starting from the just go to the previous page. Okay, wait. So you start from here and end over there. Okay, end over here. Fine. So another question. Hope you mark it while learning itself. You have to mark in your textbook, because once you complete the chapter, you won't remember what are the important questions. Okay, so then and there, when you learn, you have to mark and keep. So when you sit for learning, preparing for the exams, you know what are the important questions. Okay, so this is what over there. Next, we'll go for active metals can be used to displace other metal oxide, or reduce metal oxide to metal. Example, sodium. We'll take one example. Okay, so boron trioxide, when treated with sodium, boron treated with sodium, very simple reaction, same reaction. Just see, sodium takes oxygen or displaces boron, so we get boron and sodium oxide. So how do you get this formulas? Valency. Valence is important. Can you guess the valency of boron here? It is there in the board. Can you guess the valency of boron here? It is there in the board. Okay. So what's the valency of oxygen? -2. So this 2 could have come from here. Then 3 should have come from boron, right? So it's going to be 3 plus or plus 3, both are same. Okay, so this is the valency of boron. In this case, what's the valency of boron? 0, because freely occurring state is 0. Okay, so this is how we got the formula. Sodium is also 0, freely occurring state. And that case, you will see oxygen is -2, sodium is first group element, so valency is +1. That's why we get the formula Na2O. Okay, now we can go for balancing equation. 2 boron, 1 boron, put 2 in the front. 3 oxygen, 1 oxygen, put 3 in the front. 3 2s are 6 sodium, 1 sodium, put 6 in the front. Okay, simple equation. Practice these. If you are not good in balancing, just use these simple equations to first learn balancing. Then you can go for complicated equations. We do have tough equations, okay, in P block elements and D block elements. We'll see that, okay. So the last topic for the day is auto reduction. See, certain metal sulfide, actually what we do, we convert the ore metal sulfide into metal oxide, and then using reducing agent, we convert metal oxide to metal. But certain metals, when you oxidize them, directly they get reduced without help of reducing agent. One such example is mercury. Okay, the ore name is cinnabar, HGS, mercuric sulfide. The ore name is cinnabar. Okay, the chemical name is mercuric sulfide. So +2, -2, HGS. When treated with oxygen, it is roasting actually. This is roasting, heating process of oxygen. Sulfur combined with oxygen forming sulfur dioxide, and directly we will get mercury. You understand? So we get mercury directly. So we don't need reducing agent for such cases. Okay. So with this, we'll stop the video. Thank you, students.